In this final section, we're going to look at using an icebox. And this technique for finding equilibrium constants is going to be used in the next 3 chapters. So this chapter and then in the next 2 chapters as well. So essentially, this is a very important skill to learn. In previous sections, we did find the equilibrium constant where we were given the equilibrium concentrations of everything. But that's not always the case. Sometimes we have some concentrations and we don't have others. So this is where an icebox comes in. So first of all, what do we mean by ice? Well, we mean initial change and equilibrium. And you'll notice that I have both reactants and my product in my icebox table. And what I'm going to write is their initial concentrations, which for the product is usually 0. Their change in concentrations, how did they change as the reaction went along, and their equilibrium concentrations. Then using the Kc expression, which is products over reactants, I can solve for the thing that I don't know, the variable. Okay? So in the first example that we're going to do, we're going to have the change in concentration. In future examples that we're going to do, we'll do 2 of them, we're not going to have the change in concentration, and you'll see how that changes the math. So this is a very useful skill and something that absolutely must be practiced to be successful in general chemistry too. So let's take a look here. It says consider the reaction below. If the reaction begins with only reactants and the concentration of X is initially 0.5 molar and the concentration of Y is initially 0.6 molar, at equilibrium the concentration of X2Y is 0.084 molar. What is the value of Kc for this reaction? So as usual, I'm not going to try to solve it here. I'm going to switch over here to the camera so that I can write on it. So we have the initial concentration of X, and the initial concentration of Y. Because my writing is already messy enough to begin with, I've already set myself up with an icebox, okay? So I'm not going to write this out for you, so it'll be a little bit more organized as you're looking at it. But basically, we have in our icebox the reactants and the products, and then we have ice, initial change and equilibrium, and it's a table. Right? We're going to write the initial concentration of each thing. We're going to write the change in concentration of each thing. We're going to write the equilibrium concentration of each thing. Then we're going to use the equilibrium expression, products over reactants, in order to solve for the actual equilibrium constant for this reaction. So let's look at the initial concentrations of X and Y. Well, in this case, these are pretty straightforward because they're given. X is initially 0.5 molar, 0.500 molar. All right, I'm leaving the molar out because I have it up here. Y is 0.6 molar, 0.600 molar, and the reaction begins with only reactants. So the initial concentration of product is 0 because we don't have any, right? We begin with only reactants. Said another way, we have 0 product. At equilibrium, the concentration of X2Y is 0.084 molar. So in order to do this, we can add 0.0 plus 0.084 molar X2Y. If the concentration was originally 0 and it was finally 0.084, it means we added, the change is plus 0.084 molar. And we finally get the equilibrium concentration of 0.084 molar. Note that we are adding molarities together. You can only add molarities together if you are in the same container. Okay, and this reaction is occurring in the same container, so you are allowed to add molarities together. You cannot just take 2 random samples of water and salt water and mix them and add their molarities together. That's not how it works. Okay, so this only works because the volume is fixed or we're in the same container, however you want to think about it. But it does work in this case. All right, now let's think about stoichiometry. Okay, well, where did this 0.084 molar X2Y come from? Well, it came from some X and some Y reacted together to form this. Well, if it takes 2X to make this, right, we're going to have some less X because some X became this, right? But we're going to actually have double the amount less. So we're going to subtract 2 times 0.084 molar. Why 2 times? Because we have 2 of these forming one of these. How about y? For y, 1 forms 1. So we lost 0.084 molar of y in order to form the x2y. So it's just 1 times 0.084, or just 0.084. We can now do this math, right? 0.5 minus 2 times this, and we get 0.332 molar. For y, we can do the same, 0.6 minus 0.084, and we get 0.516 molar. So essentially, this is a math equation. You take the initial, you subtract out the change, you're going to usually lose reactants, right? And gain products. So it's going to be minus for the reactants and plus for the product. And we're going to end up with this situation here. Well, now this is the same question we had before, because we have all the equilibrium concentrations. Now we can plug into the Kc expression and get our equilibrium constant. So let's look at that. Kc equals products over reactants, concentration of x2y over concentration of x squared, because there's 2 of them, concentration of y. Plugging in, x2y is 0.084. Note that I'm using the equilibrium concentrations. Why? Because this is the equilibrium constant, so we need the concentrations when the reaction is at equilibrium. I'm going to plug in the concentration of x, which is 0.332 squared, and I'm going to plug in the concentration of y, which is 0.516. I probably don't need the times and the parentheses. You probably don't need the parentheses for this one. So basically, you get the idea there. So we take this, square it, we multiply it by this, and we divide it into that, and we find that the equilibrium constant here, Kc, is 1.5. The K's usually have no units, so I didn't bother to put the molarities in all of these cases. So here's an example where we used an ICE table where we were given the equilibrium concentration of a product. This is somewhat common because sometimes you can measure the equilibrium concentration of the product, which then allows you to back calculate the equilibrium concentrations of the reactants. Let's look at a slightly more complicated example, and an example that's definitely going to come up again. All right, all of these ICE table things you need to know how to do. The one we just did is the most straightforward case. Let's look at a less straightforward case. All right, it says, consider the reaction below. The reaction begins with only AB. AB is the only reactant, and it's 0.2 molar. The equilibrium constant, Kc, is given here, 4.2 times 10 to the minus 4. What is the equilibrium concentration of A2 and B2? All right, so we have a reaction. 2AB yields A2 plus B2. And we are told that we initially start with 0.2 molar AB and no A2 or B2. So we know all the initial concentrations. I've again made an ICE table where I have my reactant here and my 2 products here. So I just have everything in the reaction here. Sometimes you'll see these as rice tables where the reaction is included. I do them as ICE tables, but that's fine. R for reaction, change, and equilibrium. Well, initial concentration is straightforward because it's given. This is 0.200 molar. And it says we begin with only reactants, so the concentration of A2, the first product, and B2, the second product, are both 0. But here's where it gets complicated. I don't know the equilibrium concentration of AB like I did in the previous example. But I do know the value of Kc, and of course I could write the Kc expression. So let's take a look at this. These are unknowns, so let's use variables. What are we going to, how much of this and how much of this are we going to get? Well, I don't know, but we're going to get plus x and plus x. So x, meaning I don't know. It's a variable. It's something I need to solve for. Okay? Note that they're 1x and 1x because the stoichiometric coefficients here are 1 and 1. If you got 2 b's for some reason, then it'd be x and 2x. All right? So you have to consider the stoichiometric coefficients. Well, if I gain x of this and I gain x of this, how much of this is it going to take? Well, I'm actually going to lose 2x. Why 2x? Because there's a 2 here, and 2 of these forms one of these and one of these. So I'm going to lose 2x of this. So at equilibrium, it's going to be 0.200 minus 2x. 0 plus x is x, and 0 plus x is x. So I'm just adding these together, except now I have variables here as opposed to numbers like in the previous example. Here's a thing that I'm going to tell you that is not 100% true all the time. What I'm going to tell you is that we can ignore this 2x. And I'm just going to consider this 0.200. And the reason that I want to be able to ignore this 2x is so I don't have to use the quadratic equation to solve this. In some textbooks, it will tell you that if x is less than 5 or 10% of this concentration, you can ignore x because it won't be appreciable. But at the end of the day, you would have to use the quadratic equation because I'm going to have 0.200 minus 2x squared, right, in my equilibrium constant expression because it's going to be raised to the second power for AB. That would force us to use the quadratic equation to solve it. In these examples given in this book, I am not going to give any example where you can't ignore x. Okay? Said another way, you won't have to use the quadratic equation. Now, if you ever take a course called quantitative analysis, you definitely will have to use the quadratic equation. At least I did when I took that course. Okay? So this is basically a simplification if many people say if x is less than 5% of the original concentration. Let's take a look at what we can do now. All right? Kc equals products over reactants. Concentration of A2, concentration of B2, over concentration of AB squared. All right? Equals for A2, and well, I'm going to rewrite it because I have Kc. So in this case, I want to write the Kc value, 4.2 times 10 to the minus 4, just given in the problem right there. All right? Equals A2 and B2 are both x, so x times x, or x squared if you prefer, over, again, 0.200, not 0.200 minus 2x, just 0.200 squared. Okay, because I have to square this one. Now, let's go ahead and simplify this. In order to simplify this, the first thing I want to do is square this 0.200. So then I get 4.2 times 10 to the minus 4 equals x squared, x times x is x squared, divided by 0.0400. Cross multiply, I'm going to move the x squared over to the left side. X squared equals 0.04 times 4.2 times 10 to the minus 4, which is 1.68 times 10 to the minus 5. To solve this, take the square root, x equals 0.00410. What does this tell us? Well, in this case, this is the concentration of this, of both of these, because they're both just x. Note that if this was 2x, you'd have to double it to find the concentration of B. So in this case, the concentration of A2 equals the concentration of B2, which equals 0.00410 molar. Remember, the original job was to find the equilibrium concentration of A2 and B2, which we have done in this way. One minor math thing that I want to point out, when you took a math class, you learned that this equals plus or minus this, right? Because if you square this, if it was negative, you would also get the same number. You can ignore the negative answer here because you can't have a negative molarity. It doesn't make sense. So we reject the answer that doesn't make sense. One more example, same thing, just a different example. Now we have a real reaction instead of A's and B's, okay? It says, consider the reaction below. The reaction begins with only CO2, which is 1.2 molar. And the equilibrium constant is given as 8.30 times 10 to the minus 6. There should only be one minus sign there. All right, what is the equilibrium concentration of H plus and HCl3 minus, so protons and bicarbonate? So Here's a little bit different ice table that hopefully you remember from previous lecture about why this is the case. It was earlier in the chapter. Here we have CO2, we have H plus, and we have HCO3. We don't have water. Why don't we have water? The reason we don't have water is because water is a liquid. So we only put things that are gases and aqueous into our equilibrium constant expression. So therefore, we only need to put those in our ice table. Okay? So we are told the initial concentration of CO2 is 1.20 molar. All right? The initial concentration of H plus is 0. And the initial concentration of bicarbonate is 0 because we begin with only CO2, so there are no products when we start the reaction, there's only reactants. Change. Well, in this case, we have 1-to-1 stoichiometry. We do not know how much H plus or HCO3 minus we have. That's the whole idea of this problem. What is the equilibrium constant of concentration of H plus and HCO3 minus? So we're going to get X of this and X of this. Again, they're both 1x because the stoichiometry is 1-to-1. So in this case, we want to have at equilibrium x of this and x of this. How much CO2 are we going to lose to get x of H plus and x of CO3 minus? Well, we're going to lose x. Why 1x? Because the stoichiometric coefficient here is 1. In the previous example, it was a 2, so we lost 2x, but in this case, it's only 1. So we have 1.20 molar minus, I'm not going to put the m's, I don't know why I'm doing that, minus x. Okay? Remember that what I said before. In the examples that I'm going to present, we can ignore the x so we don't have to use the quadratic equation. Even here, even though this isn't squared, I'm still going to end up with an x squared term, and I'm still going to end up with an x term, which means I'd have to use the quadratic equation. To simplify the math, this is already an important thing to learn, and this applies to many other chapters, and I'd rather focus on this than focus on learning the quadratic equation. So what we're relearning the quadratic equation. So what I'm going to do is I'm just going to call this 1.20, and I'm going to ignore this x. I'm going to assume it's 5% less, or as I'm telling you, I pick examples where it is 5% less. Okay? Less than 5%. So let's take a look at this. We need to write the Kc expression. So Kc equals products over reactants, concentration of H plus, concentration of HCO3 minus over concentration of CO2. I don't know why I wrote this in the middle of the paper. I'm not giving myself a lot of space over here. I should have written it over here. Anyway, note that water is not in this expression because water is a liquid. Only aqueous and gas go in this expression. I know the value of Kc. It's 8.30 times 10 to the minus 6 equals concentration of H plus is X, concentration of HCO3 minus is X over 1.20. All right, cross multiply, bring the x's together and put them on the other side. And we end up with x squared equals 8.30 times 10 to the minus 6 times 1.2, which is 9.96 times 10 to the minus 6. How am I going to solve this? Take the square root, take the square root. X equals 3.16 times 10 to the minus 3. So, because the stoichiometry is 1-to-1, like in the previous example, the concentration of H plus equals the concentration of HCO3 minus equals 3.16 times 10 to the minus 3 molar. These ice tables are incredibly important moving forward. So it's really important that we practice with these.